Okay, everyone. Hi, I'm really excited to be here today to talk about some of our results on estimation-theoretic tools for security and privacy. This work was done in close collaboration with Muriel Medard at MIT and Maya Kavaria at BU. And the goal today is to introduce basically one tool from estimation theory called the principal inertia components that we find is particularly useful for problems in security and privacy, particularly from the information-theoretic perspective. But before I go on and introduce the principal inertia components, I want to motivate it by introducing a privacy setup that we're going to be looking at today, and also mention some previous work that we've done in the area. So today I'm going to be talking mostly about privacy, and in particular privacy in one specific model, the simplified model that we're going to be looking at today called the one-shot release model, where we assume that we have a random variable x that's transformed through a randomized mapping into another random variable y, which is disclosed to an untrusted party. You can think about x as your data. For example, x are your movie ratings, which is transformed by a privacy-assuring mapping that could be like adding noise to your movie ratings. That's disclosed to an untrusted party. And you disclose this data in order to receive some utility from this data. So for example, you want to find recommendations of new movies to watch. But at the same time, there's some other information here represented by the random variable s for secret, that you want to keep private, some private feature that's correlated with your data. Think about it as your political preference that's correlated with how you rate movies. And you don't want your entrusted party to be able to have a reliable estimate or to be able to guess this secret feature. And the privacy goal here, and the overarching goal, is to characterize the optimal privacy utility trade-off for different privacy metrics or for different utility metrics, and to understand how that depends on the joint distribution of your data and of your secret. And the engineering goal here is to design this blue box. The engineering goal is to design a privacy-assuring mapping that distorts your data in such a way that you can still achieve a certain desired level of utility while still assuring privacy. So there are many ways of formulating this problem. One way of formulating this problem fits into this general setup here, where you formulate it as an optimization problem. So for a given privacy measure, here I am just denoting it by FP. This is a general measure. I'm not specifying it yet, which measures the privacy between S and Y. It's a property of the joint distribution. You want to minimize this privacy metric subject to some utility constraint. Think about it as a distortion measure of how much you distort X to Y. You want the utility to be higher than a certain threshold. Then the problem of finding this blue box, given that you know something about the joint distribution, boils down to solving this optimization problem here, to minimizing the privacy threat subject to the utility measure. And theoretically analyzing this optimization problem, we find the optimal trade-off between privacy and utility for these metrics. And alternatively, you could do the opposite, right? You could try to maximize your utility subject to a privacy constraint. And just to make this clear, theoretically, the goal would be to find a set of achievable pairs for different privacy metrics. And in particular, the engineering goal is to design these randomized mappings. So one particular instantiation of this problem that has been studied in the past in the literature is that you measure privacy as the average information that Y carries about S in bits. So the average mutual information between S and Y, you want to minimize it, subject to a certain expected distortion constraint. This is an average result and tries to minimize how much you distort this data for a given distortion metric. This set of problems is interesting because you can then formulate the problem of finding this optimal mapping into solving a convex optimization problem, and this has been applied to real-world data sets. Another formulation of this problem that I find particularly interesting is the privacy funnel. If I have time, I'll talk about this towards the end of the talk. I don't really think I'll have time for that, but let's try. Where here you have a measure of privacy and utility that only depends on the joint distribution of S, X, and Y, where you're trying to minimize the average mutual information between S and Y, while maximizing the information that the disclosed data carries about X. This problem is non-convex, but possesses very interesting information-theoretic properties. So it's hard to solve, but there is some interesting things that we can say about that, some very fundamental things. And hopefully I'll have time to talk about that. But the main focus of today will be a slight variation of this model, where we're measuring privacy and utility in terms of MMSE, of minimum mean squared error, on how well the adversary the interested party can reconstruct S, and utility is measured on how well he can reconstruct certain properties of X that we want to disclose. So if you don't know what MMSE is, I'll define it a little bit later. This is, if you come from the signal processing field, this is some pretty standard definition. But the goal of privacy here, and the setup that we're going to be looking at today, is that we're going to assume that S is actually a collection of features of your data X. So think about it as a set of functions of your data that you want to hide. So, and we measure privacy in terms, you want to maximize the minimum mean square error of the adversary reconstructing each of these functions. So you don't want the adversary to be able to reconstruct it with a quadratic distortion smaller than a value theta. And at the same time, you have some other set of functions, G is for good functions, so a collection here of functions that you want the adversary, to the interested party, to be able to correctly recover. So you want the maximum distortion of these functions to be upper bounded by a certain value delta. And in the analysis that I'm going to show, we're going to make another assumption that we want the data that you have originally and your disclosed data to have the same distribution. And the reason for this is because oftentimes in practice, we use this data to train machine learning models, right? And the way we train these models and the final values that we're going to find depend on the distribution of the data. So what's the motivation behind this setup of measuring privacy in terms of these collections of features that we want to hide and how well the adversary can reconstruct it, and utility in terms of how well he can reconstruct these good features? So the motivation comes from a very practical motivation, and this is a problem that I face almost every day, for example, at IBM, is when you want to share data with an untrusted party. So for example, assume that you have a company, and this company wants to hand data to a business intelligence company. And why are they handing that data to them? Well, because they want analytics and business insight from the data that they're getting. So for example, you're revealing customer information, and you're asking this company to train a machine learning model on that, and maybe pinpoint customers that you should send target advertisement, or maybe tell you something about how to improve the operations of your business. So you want to review, so for example, if this data set includes information about customers, let's say you want to review population statistics, you want to be able to train these machine learning models, so you want to keep you want to preserve the distribution of the data. And there are certain good features that you want to have available for analysis. You want to ask the business intelligence company to pinpoint certain, say, customers that you should send some advertisement to. But at the same time, there are certain attributes that you don't want to have revealed to the interested party. For example, this may be personal information about your customers. This might be something that reveals operational information about your business. So the way this would looks like something like this. The motivation is really to disclose data that reveals overall population statistics of a data set while still disclosing or suppressing information about the individual samples. This is important. We want to reveal population statistics, but we want to reveal limited information about individual samples. So this is what a data set would look like, right? So assume that you have a certain set of samples, x1 to xk. We assume for the rest of the talk that these samples are IID, and they're drawn from a finite discrete alphabet. And you have a certain set of features that you want to hide, the secret features, a function of which one of these samples, the sensitive features. You have another set of features, the good features, that you want to disclose. And just to make this clear, the goal is to design this privacy assuring mapping. Basically, it's a randomized mapping that's going to distort each of these samples individually, so that given the sample y1, I have a hard time reconstructing the sensitive samples, the sensitive attributes S, but at the same time, I can reliably reconstruct the good functions X. And you can assume already, you can already foresee that depending on what these secret features are and what the good features are, you're going to have a trade-off between privacy and utility. And in order to capture this trade-off, we arrive at the star of the show today, which are the principal inertial components. Principal inertial components are very interesting creatures from the information theory, statistics, and mathematical probability fauna. And they can be used to address several problems in privacy, but also other problems in information theory. So what I'm going to do for the rest of the talk is that I'm going to give you a brief overview of some definitions and properties of the PICs. What are they? Then I'm going to show how we can design privacy assuring mappings based on the PICs for this problem, for this privacy setup I just motivated. And if I have time, I'll talk also about how they reveal the fundamental limits of perfect privacy in this one-shot model. Basically, we can use the principal inertial components to determine when can we disclose useful data with perfect privacy from an information theoretic perspective. Okay, so let's start off with the definition and properties of the principal inertial components. And the principal inertial components, they show up by looking at the underlying estimation theoretic problem behind the privacy problem that I just mentioned, and asking the question, what can or cannot be estimated from noisy data? Okay, and we ask this question, as I mentioned, in terms of minimum mean square error. So if you can't remember exactly what MMSE is, this is a quick refresher. So assume that you have a hidden random variable x. In the previous case, x was our data, and we have some observed value of x, some noise observation of x, y, which is your observed variable. And given an observation of y, we want to reconstruct a certain feature of x, represented here by function f of x. And how do we reconstruct it? Well, we reconstruct it in order, you want to find an estimator of f of x that minimizes your expected square loss here, your squared error. So it's not very difficult to show that the optimal estimator in this case is your conditional expectation, right? This is standard result in estimation. It's expected value of f of x given y. And then the minimum mean square error, which is the minimum reconstruction error that you can have in terms of this squared loss, is given by this expression here. I'm not going to dwell into what this means, but just for the experts out there, the principal inertial components will turn out to be the spectrum of this conditional expectation operator. But I'm going to give you a little bit more, another definition that's a little bit easier to grasp, which is the following. So this is minimum mean square error. We want you to find what is the function of the hidden variable that we can estimate with the smallest square error. And of course, we can always estimate constant functions, right, from an observation. That's trivial. If the function is equally this function is the function that maps x into 0, we just output 0. So we're going to assume that this function has 0 mean and unit variance. And again, the question that we're asking is, out of all functions of x that have 0 mean and unit variance, what is the smallest MMSC that we can achieve? What is the function that is the easiest from this quadratic sense to estimate, the one that can be most reliably estimated? And if you solve this problem, the function that you're going to find, you're going to denote it by f1. And the solution of this is 1 minus lambda 1. This is the MMSC that you achieve. And the lambda 1 is your largest principal inertial component. So you can solve this problem again. Now that you have a function that you know what's the easiest one to estimate, you can ask what is the other function that's uncorrelated to the previous one that we can reliably estimate. And that if you solve this optimization one by imposing this new constraint, that you solve this optimization problem, you get the second largest principal inertial component as an output. And you have another function here, f2. You can think about them as a singular vector, singular value pair. And again, by imposing these orthogonality constraints, we recover these basis functions f and all the principal inertial components. So this decomposition is very useful for understanding what are the properties of a hidden variable that we can estimate. So just introducing a little bit more notation here. Again, this is a little bit redundant because for the purpose of this talk, I'm assuming that all the random variables are discrete with a finite alphabet. But denoting by L2 the set of all functions of x, real functions of x that have over the support of your random variable x that are real. This decomposition gives you two things. First, it gives you a set of basis functions for the space. Right? So denoting by f0 the constant functions, you find functions f1 to fd. And these set of functions, they form a basis functions for the space of all functions of your hidden variable x. And for each one of these functions, we get a second thing. We get a singular value, which is your principal inertial component, which represents how well we can reconstruct each of these functions in this basis. OK, so let's just go back to the estimation problem that we were asking that is related to privacy. So if you give me a target function of a hidden variable, right? If you give me a target function and we want to determine how well we can estimate it, we can decompose this function in terms of a weighted sum of the basis functions. This is pretty standard. And the MMSC of estimating this target function can also be written then purely in terms of the principal inertial components and this decomposition in terms of this basis function. And when we apply this to the problem of privacy, and the key idea of applying this to the problem of privacy is the following. The key idea is to design a privacy assuring mapping such that the resulting basis, f1 to fd, and the resulting principal inertial components satisfy our MMSC privacy and utility constraints. So we're going to try to find the mapping such that these basis functions satisfy our privacy and utility constraints. So you might be wondering, I presented the principal inertial components as the solution to this optimization problem. You might be wondering, how can we actually estimate it from real data? How can we compute it, at least if we know, for example, if we know the distribution? This is just a glimpse of how you do that. You can form this matrix Q, the matrix whose entries are the joint distribution of x and y, divided by the square root of the product of the marginals. And if you take the singular value decomposition of this funny matrix, the left singular vectors are the basis for your MMSC decomposition. And the diagonal values here are your principal inertial components. Okay, and just to mention, we're of course not the ones that are proposing this. There's a long history of studying the PICs that date from the mathematical probability literature, dating all the way back to Rényi, for example. And there's a growing interest in it from the information theory community, particularly in the context of strong data processing inequalities. And there are statistical methods available for estimating the principal inertial components. And what we bring to the table is applying this, as I mentioned, to the problem of privacy with estimation guarantees. Okay, so these are the principal inertial components. The principal inertial components give you a complete description in terms of this quadratic loss of what functions of a hidden variable you can or cannot estimate. So how can we use them to design privacy assuring mappings with estimation guarantees? So just going back to the setup that we were focusing in the beginning, we have our data and we have a set of features of our data that we don't want to be reliably reconstructed from whatever we disclose. And there are another set of features, G, that we want to be reliably reconstructed. And I'm going to give you a proof in pictures of how we do that. So the key idea is to design this randomized mapping. We're going to engineer it now that transforms your data into your disclosed data Y, such that the principal inertial components act in such a way that the functions that we want to hide are attenuated. So the basis functions that correspond to the functions that we want to hide have small principal inertial components, and the ones that we want to reveal will have high principal inertial components. So basically what you're going to do is something that looks like this. You're going to attenuate the functions that we want to hide. And this reveals the nature, what's at the heart of the privacy utility trade-off in this estimation-theoretic setting. What it says is that if the space spanned by the private functions, by the functions that you want to hide, isn't correlated, is orthogonal from the space spanned from the useful functions, the ones that you're going to disclose, you're going to have a favorable trade-off between privacy and utility, because you're going to be able to design these mappings such that you hide the private functions while preserving the information in the useful functions. On the other hand, if there's some overlap between them, and this is very intuitive, if what you want to hide is correlated with what you want to disclose in order for you to get utility, you're going to have a bad trade-off between privacy and utility. And in particular, when you're designing this mapping, regardless of how you do it, the principal inertial components will attenuate the whole thing. So if you want to hide your functions, you're also going to have to hide that which you want to reveal for the purpose of utility. So, and we can actually do this in practice we can actually formulate in the problem of designing these privacy assuring mappings in terms of an optimization problem. This is a standard convex optimization program. Of course, I don't expect you to understand this. If you want more details, you can look at our papers. But I just want for you to think about this as an optimization block based on the principal inertial components that can be fit into a more general data-driven program for finding these privacy assuring mappings. So just think about this in terms of a black box. And how would you do this in practice? Of course, this is a simplified version of how you would do this. There's other considerations that you would take into account. But you would have a reference data set. You would use that data set to have an estimate of the joint distribution of your data and what you want to hide. And you would plug in your utility and privacy constraints to this PIC-based optimization, this PIC-based convex program. And you would plug it into a standard convex solver, which will pop out a privacy assuring mapping. And you can accomplish exactly that, what we set off to accomplish in the beginning. For each of your samples X, you can distort it according to this mapping and get the sanitized data Y. So I won't have time to go into this last part on the principal inertial components and how they're related to the fundamental limits of perfect privacy. Just going to give a 10-second overview to say that the PICs capture the fundamental trade-off between disclosing private and useful information in this private funnel. So it answers the question, when can this value of t be positive? When can we disclose a non-trivial number of information bits about your data while perfectly hiding that which we want to keep private? So you can use the principal inertial components to analyze this problem. So I'm going to skip that and go directly to the final remarks. So the PICs are useful tools for creating practical optimization problems for finding privacy assuring mappings. And they also play a role in characterizing the fundamental limits of perfect privacy. And in other work, we have shown that you can also use them to characterize simple information-theoretic properties of crypto systems with small key size to make information-theoretic claims about what is hidden in your system when the key is small, when the key is smaller than the message, for example. And the end goal of all of this analysis is really data-driven privacy with information-theoretic guarantees, is to create a set of tools that can augment current privacy methods, for example, differential privacy, so that we can find privacy assuring mappings that achieve a good trade-off between privacy and utility. And I personally think, and hopefully if you're interested in this, come talk with me after the talk, that there are many interesting tools from information and estimation theory that can be applied in this setting. Thank you.